Good afternoon, everybody. So let us start our lecture today. And today is October 5th. (2021), and as we are discussing red, blue, red, black. Sorry, so red, black tree. So one of the common interview question is that in a red, black tree, in order to be red, black tree, is it required to have a red node? No, right?
We saw yesterday there was you're making
Yeah.
one entirely black.
Okay, that's good. So as I said, then in order to understand red black tree, is better if you understand AVL tree first. Okay, so AVL tree is implemented first. Okay, but somehow from my syllabus content, AVL tree got deleted. It should be here. Okay, I will add it here. Okay, I uploaded quiz maybe 3, right, today, and quiz 3 and assignment 3. These are due this weekend. Okay, so please take it as soon as possible. And this week we are discussing red black trees, and if you go to D2L, you see that I uploaded a red black tree.
Red and black trees, because I think there might be something wrong with it.
So presentation you cannot pull up?
Yeah, it's like unexpected server response. Maybe get a real one.
Let me see. I can do it.
Okay.
Click over here and then download. Click over here and then click on this here and then download. You got it? Okay. I'm giving you my PDF file so that if you find something better from some other place, you can add or edit this PDF as your own. I will open it from okay. So in our last lecture we discussed insertion with simple example. Insertion with an example in a red black tree. So let me recap quickly. How many rules, how many properties are there for a red black tree? 5. What is first one?
Root node is black.
Root is black. Number 2, every node is either black or red, and then all leaves are black and nil. Okay, that is number 3. Number 3 or 4?
3.
Okay, what is number 4?
If a node is red, its children must be black.
Yes, if a node is red, then both children are black, right? But its opposite is not a restriction. If a node is black, then it's either children, either one or both can be black or red. And what is the last one? What is the last property? Number of black nodes in a wall path, in every path, same, right? Equal, right? Equal number of black nodes. Okay. So here we started from last week. Let me recap this one quickly. So insertion, if you get 1. So if you understand this, you can do in any order, but for any, so we are here, we have in order, data is coming in order, but later we saw that order will not persist. It will be changing. So 1, so what is the first rule? How do we start? Whenever you get a node, a newborn node is always red, right? A newborn node is always red. Then starting from red, then we will ensure the all of 5 properties. Since this is the only one, so we will make it black because this is the root, so it's black, right? Root is always black. And then you think that there are 2 leaf nodes, but okay, we don't need to draw leaf nodes for simplicity. Okay, it maintains all properties. Okay, then when you get 2, right? Another node through 2 will be okay. A red black tree is always a binary search tree, right? So 2 will go the right side. Okay, so then 2 it will start from red, and it will check the condition, the 4th condition, right? 4th condition, if a tree, a node is black, then fine. If a node is red, then restriction, right? So number 2 is fine. When you will insert number 2, there is no problem, right? So 2 as is. So now when you insert 3, so initially we insert 3 like this way, what will happen? 3 is red, right? Initially it will be red, newborn, and then it will check up its parent. Its parent is red. So now number 4th condition, if a parent is red, then child must be black, right? So then we can do this way, can change this way, the number black. Okay, now since a red black tree is also an AVL tree, okay, so we need to ensure that, so we need to make a rotation, right? So here it says that still it does not. Why do we need rotation? Because still it does not maintain. Does it maintain the 4th property is red, then black? One is black is fine. Okay, but what is the problem over here?
It's not balanced.
It's not balanced, right? On the right side there are 2 black, and the left side is 1, right? So we need to balance it, right? How do we balance it? Make a right, that left rotation, right? So then it's number 3. Okay, now if we make a left rotation, then what is problem?
The root is red.
Yes, the root must be black, right? So when last step is here, root is black, now it is solved. Okay, so this is a red black tree, and there is no red.
Okay. I understand like each step what condition was violated and why you fixed it, but like the order of the steps seems arbitrary. Like why didn't you at first just rotate it because it violates AVL? So do you always check the red black conditions first and fix those?
So you said instead of going steps 2, you will go step 3.
Yeah.
So let us see that if step 3, then it will be root, then we'll see if it will be red, right?
Yeah, that would be.
If it is red, then red, so then make it black, and then this is, I think that should not be a problem.
Well, if you have 1, 2, 3, the first step, and then you said, oh, it violates AVL, then it'd be 1, red 2, red 3, and then you
So
said
today,
the 2 violates
I-
being red.
I understand your question. Today we will go through the cases. There are 3 cases.
Okay.
In algorithm, when you write an algorithm and pseudocode, there will be, or in program, there will be if else if conditions.
Okay.
So in if and else if condition, no matter how, which order you place, if else if, all condition will be checked, right? I skip few slides. We'll come back.
Okay.
We'll go back there.
So we're first checking the
Yeah.
red black, then checking AVL.
Yeah, I think it's not be a problem, but
Okay.
because we will see soon, I will go back because I skipped something. Let us understand this, then I will keep, instead that I skip some algorithm actual algorithm I skipped. I will go back, then we will understand. Okay, and through this way, we see that when we insert some elements, then we are getting like this way, and then, so that the slides are self-explanatory, I believe. So these are one by one. So I think if you go through this, then you will be able to find this. Okay, but for now, the last one. So over here, let us check. Okay, so there is a mistake over here. It should be red. Let us check whether it is a red black tree or not. Let us check all 5 conditions, right? The root is black. First condition is done, right? The last condition is 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, right? So the last condition is met, right? And if a node is red, then both children are black, right? So here for 8, and then if your node is black, then it's fine, there is no issue. So all conditions met over here, right? So this is a red black tree. So initially, although we got data in sequential 1, 2, 3, 4, and but however, if we say that here we are getting in not in order. Okay, now so in order to get the result in an ascending order, in order to get the data in ascending order, so we discussed 3 traversal order, right? For a binary search tree, BST has 3 traversal order. So which order I need to do in order to get the result in ascending order? In order to get the data in ascending order, which traversal I need to do? In order, yes, always in order, right? So in order means that root will be in, right? Then 1, 2, 3, then 4, then 5, 6, then 7, 8, then 9, 10, 11. Okay. Now everybody take a piece of paper and pencil. Okay. Now if I want to rotate this, if needed, we will see that we need rotation. Okay. So we saw that in last lecture there are 2 rotations, left rotation and right rotations, and in addition to this rotation, left rotation, right rotation with perspective to branches. So here if you consider 6, okay, after 6 from 8 this is a branch, and from 6 it has 3 branches, 5 itself is a branch, and starting from 4 is a branch, and starting from 8 is a branch. So if we rotate from 4 to 6, what will be this shape when I rotate? Left rotate. Who can draw?
So
Draw it.
The 6 where the 4 is.
Yeah, so it will be hanging on 6.
Okay, then we would have 6 with 3
Draw it.
children.
Draw it.
Okay. So without cutting anything yet, right?
No. It need to be reshaped. Whenever you draw it, redraw it, it need to be reshaped. So in your test, I will give you some this kind of graphs, and I will ask you to rotate at some point. Please practice. And if you have any question, then you can. I'm asking that it's easy that we're gonna hang on. We can do many rotations. We can hang on 8, right? And we can hang on 6, but let us do 6.
like we cut and then re-string? Is that
Yeah.
what we're doing now?
Did you, yeah. If you understand, did you try with a piece of paper and string at home? If you understand visually, then fine. If you don't understand, I ask you to, you can practice this demo at home. Take some piece of paper, write a number and use some string. Hang on. Okay, so let us rotate it, make a left rotation. Okay. Where x is 4 and y is 6. Consider x equal to 4 and y equal to 6. Then make it a left rotation. 1 y.
I think I understand what you're asking. You want us to switch the 6 and the 4. Oh, you
Yes.
mean, do you just want us to finish inserting 11? No.
No. You think about this insertion. It's already done. But I'm gonna make a rotation. Okay, so this is BST, right? If it is 6.
Yeah,
then
and
right
that can't be
four.
larger. Right now, it can't be.
Both. We have to make combination. In our last lecture we discussed the 2 rotations, left rotation, right rotation. Down. Yes. Okay, after the rotation, tell me that whether is it a RB, G,
I realized I just did it.
is it a reflection? Or you need to color? Or if you don't have any red pen, then what you can do? That sometimes I did. So if you don't have only one pen, then put R over here, okay? R means red, and then B is in black. R means red, and means red.
Centers, 5 rows.
Maybe they combine one.
Either then or
You did not write the one of the use is always black. Root is always black.
Oh, okay.
Right?
I'm working on it. Yeah.
68745. Yeah. Now tell me that.
Yes, I
Is it a red battery?
yes.
Tell me put R over here. Put R. Answer. So please practice some. Okay, in your test, I will give you some questions like this. If you do not practice ahead of time, you will not get enough time during your test time to study and then. So what you can do, if you don't have a red pen and pencil, then what you can do, type in R over here. Even it's black, Even you have black color, put R over here, then R over here, and then R over here. So then you will understand this is red and this is black. Put B over here, this is B, and this is B, and this is B, this is B, this is B, this is B, and this is B. And by counting, okay, so after rotation on 6, is it a red black tree again? One, two. Black, black. 1, 2. And this way, 1, 2, 3, 4. This is not right. So now this is the black tree. Tell me why. Yes, yes. How many? Yeah.
This is make the rotation. Yeah, what's after? Oh, I haven't figured out the first rotation is.
You got it?
Yeah.
This is 4 or 1?
4.
You got it? This is red, this is red, right? Number of black, this black 2. This is 1, 2, 3, 4. So that's black, right?
Right.
Last 4 of them is black. So, is it 5?
Yeah.
No, this is 5.
No?
Okay.
I thought it like moved to children.
No, no. I spent a whole last lecture to discuss this. I uploaded the video, okay?
Good.
This was the recorded video that I discussed in last lecture. I'm telling you, for sure you will get some test question. If you do not practice this ahead of time, you will not get enough time in your test to read the book and understand and to write, okay? Okay. So now, for instance, what happens if I hang on 8 and 8, right? So what is the condition to hang on a point? It must have say 6 equal to x. If you put x over here and then y over here, so if you do left rotation, then we need to have a child of 6. We have a child of 6, 8. Then it is possible to hang on 8, left rotation. Okay, practice it at home, okay? Then next in our next lecture we will discuss delete, okay, deletion operation. But now with this anecdotal example we saw that how a red black tree is built, okay? But actually there are 3 cases, okay? There are 3 cases we applied, and now let us see the algorithm actually. So insertion sort algorithm, at the left rotation and right rotation, we need to understand this, okay? In our last lecture I discussed this.
Can you check to see if I did the rotation right?
Anyways.
I think it would rotate like that. With those ones being red.
Yeah, 6, 4. Yes,
Okay.
correct. Now is this a red black tree?
No, because this one is like there's too many black nodes this
Yes.
way. Okay.
Yes. One point.
So
One of the
condition
properties is
5,
invalid, then is invalid, right? It's not a
unequal number of black nodes on the
yes.
paths. Okay.
Yeah. Okay. So now let us recap the entire algorithm for the insertion. Okay. So insertion, as we saw that in our example, the illustration, that a node is always start with a red, right? Newborn node is always start as red color, right? Then gradually it checks with its parent color, right? And it also checks the number of the black nodes. Okay, and then it changes its own color sometime, or it changes its parent color. And we saw that with that example, there was a small tree with a few 10 or 12 data elements, 10 maybe. But what happens for inserting a large data set? We cannot do it manually, so that there is algorithm. So in the book, the algorithm, it says BR, that RB property, RB. This is called RB algorithm, this red black tree algorithm. Okay, so red black tree algorithm, so these are the properties that we discussed. And mainly, let me come up here. So it's the algorithm, the book algorithm has a red black tree insert fix up, the algorithm name is. We can give any name, but okay. So the book has this red black insert fix up algorithm. Okay, so the algorithm, if we open the book, it has 3 cases. You see that? Okay, so the algorithm here, the red black tree algorithm. So this is algorithm is over here. So this part up to this part is straightforward, but here at the end, you see there is another algorithm, another procedure over here. It is calling. So here T is a tree, and G is a new node. Okay, so here the initialization, I think this is straightforward. So if you go through this, and then here I'm going to explain this one. So what happens, they are inside up to this point, so before you come to this fix up to this point, it applies the general procedure, that it applies the red is newborn node is red. Okay, and then it makes the balance using RVL tree. Okay, and after that inserting that one. Okay, and then since it is a binary BST, it will put on the either left side or right side. That will be applied over here. But here after insertion, it will check up whether there is any violation of any of these properties. So that part of the algorithm is called insertion fix up. And insertion fix up algorithm is here, and it has 3 cases: case 1, case 2, and case 3. Okay, so now let us spend some time to understand this. So in this algorithm, either you read this or you see that this.
What does the code, everything above 17 on the other slide, does that correct AVL? Like, does that make
This
sure
one?
that it's AVL balanced?
This one?
Yeah.
Yes,
all that.
yes. It
Okay.
will make that one ABL. Okay. Then whatever it will make it ABL, and then you see that it will make the color red. And here the problem is over here. Okay. So then I'll help you to understand. Here you see the P. Here T is a tree and G is a new node. And here if G dot P. Okay. I said G dot P dot color. That means P is parent. read aloud this way: parent, if the color of parent of G, you can write it down, okay? That means while color of, dot means off, right? In OOP, object-oriented programming, we use dot operator. So dot means off, OF, off, preposition. Color, if while color of parent of G. Okay. So for instance, if we insert 5, okay, maybe we do have something. So I need to change the color. So let us think that it is 4 and it's the root, okay, and then if we wanna put 6, so for instance 6 over here. So while, so this is G, okay, if the G, the parent, who is parent? 5 is parent, right? This is 5 of if, while G, color of P of G, color of parent of G is red, right? So this here in this condition is met. And if you see from here over there on the right side here, if G dot P dot P dot left, that means if G, color parent of G equal to is a left parent, parent of G equal to G dot P dot P dot left. That means if parent of G is a left child, so this means actually grandparent, left of the grandparent. So here P, so think about this way: this is G, this is P, and this is P dot P, parent of parent. For perspective of G, okay, so this is for G, this will be parent of G, okay, and this will be right side, right? This is right side for this one, so that means this will be, and this one G dot P dot P dot Y, that means it is right branch. So every parent anywhere, right? Every parent, that is the left and right. Okay, so this right means if it is in the right side, and this left means if it is in the left side. Okay, now if we understand these basic things, now we can go ahead and we can read through and then we can understand. Okay, so it's better in the book. I think if you need to go through the book over here, if I can take a and yeah. You see over there? Okay. So here this is the case 1, case 2, and case 3. So this case 3, all case 1, case 2, and case 3 is false, because the book has like good explanation that it has case 1. So this line, these are the steps for case 1, and these two are 2 lines for case 2, and these 3 lines for case 3. Okay. So since we know a demo how to do that, okay, now it is fix up, how to fix the recolor. Fixing over here, either recolor or is called rotation. But this rotation is not an AVL tree rotation. This rotation is for red black tree rotation with the branch. So now let us go to this one. It's a problem that I cannot see. Okay. For A, for this part A, okay. So the node of G after insertion. So this one is G. 4 is G. Okay, like for instance, the originally, think about that, originally it was like this. Originally the tree was like up to this. Originally at some point the tree was like something like this.
And Z was the one you inserted.
Yes. So here originally, let us see that whether the original tree was a red black tree. If the original tree was not a red black tree, the insertion will not work, because every phases wherever we are inserting, we are checking, ensuring that this is a red black tree, right?
Assume that the tree
This
you're
is,
inserting to was
yes,
already
up
red
to
black.
this point it is valid. So you see that this one, this is root, and then 1 2 1 2 1 2, and then we see that is red, all black. Okay, this is black, all red, no problem. This is black, so this side is red, no problem. This side is black. And if it is, the condition is the mainly if it is a red node is black, then both children are red, then both children are black. Okay, so here the all condition met. Now we are inserting 4, right? So we are inserting 4, then 4 is less than 5. So now 4 will go to the left side of 5. Okay, now we need to consider, we need to check first of all. So this is red, initially red, right? And then we know that the first rule that if its parent is red, then its children cannot be red, right? So then we need to recolor. We need to recolor. For instance, here, there, from here to here, we are recoloring parent. Okay, so we are recoloring. Sometime you may recolor the node itself, and sometime you may recolor the parent. So recoloring node itself, it goes not in fix up, it goes about the other part. So now let us see that 4. Okay, so we are keeping 4 as is red, and then we are recoloring is 5 to black. Okay, and if we make 5 black, right? So then and then also the problem will be over here. So the problem will be over here. What do we need to do? If it is a, what I'm doing, initially G was over here. Initially G was over here, and we need to check this sequence all the way from this leaf to all the way root. Okay, and here whenever we are, if for instance, if let us think that the problem, if it is red,
So it's like recursive, you have to check the parent, then the parent's parent.
for instance, initially think that if it is red, okay, it was red, right? The 8 was red, right? What happens if 8 was red? Then what would happen? Then it definitely mismatch or violate at least one of the properties. Okay, so in order to fix that, so we need to do this color also. We need to check this one. This one is happened for the condition for the case 1. Okay, I'm going back to algorithm, and over here you see that, and then G was over here, then G will be parent of parent, this will be grandparent. Now G will be over here, then it will assume that number 7 is inserting as a newly, because number 7 originally, previously it was black, right? But now it become red, right? So that the in an AVL a red black tree, it has all properties combined, integrated. Okay, so at any point. So now you need to go from here you need to check from here to up to previous point, and what will happen at this point, you see that there is a rotation needed. Okay, and you see that there is another rotation over here. Okay, so that all steps, the algorithm, it discuss the condition from here. You see that only we are inserting 4. Okay, only we are inserting 4. Then after inserting 4, what happens? The shape from starting from this and ending it here, the original shape is completely different, right? This is fixed up. And number these two, case 1 and these two, are intermediate steps. Okay, so after here, so originally this was original, this was before insert 4, and after insert 4 and fixed up. Okay, and these are intermediate steps. Okay. So over here, intermediate steps, in one phase it falls case 1, and in another case 2, and in case 3. The slides has differently case 1. See the case 1. Case 1, if G is uncle, there is G. If G is uncle, Y is red. Here is G and uncle is Y. Uncle means parent's brother, right, or sister. Parent brother, right? So here G, and then it is, we need to look at the parent. Okay, so you see the steps. If this happened, then we need to do these 4 steps. First of all, color parent of G. If parent of G, we need to make it black. Okay, and then color Y. This is the uncle of G to black. Uncle of G is to black. Okay, so and here the first step, parent of G, already parent of G was A. Sorry, parent of G was A. Make it black, and then also make it uncle is black, and then make it parent of G. That means grandparent of G, red. So grandparent of G over here, this one, grandparent of G is C. Okay, make it C is red. This is make C is red. Okay, and then move G equal to grandparent of G. That means this point, this will be G. All these 4 steps should be maintained for case 1. I don't have time, but let me go quick. Give me a few more minutes, please, so I can go. This is for case 1 and for case 2. Case 2 is if G's uncle Y is black. In that case, what we need to do? Okay, in that case, and we need to do a left rotation. Okay, left rotation on G. Okay, and then case 3, if J's uncle Y is black, then we need to do parent, make the parent black, and we need to make the grandparent red, and as well as we need to do a right rotation. Okay, so you see that in the slide it has step by step for all these 3 processes. So please read the slides and then go through these 3 slides for 3 cases first. Then go to the algorithm back, then you will, hopefully you will understand this. Okay, because the algorithm here in the slide, it has concise, it has case 1, it is case 2 and case 3. The whole algorithm, the book algorithm has whole steps, okay, but it has maybe in pseudocode format. Okay, so please start reading it and try to understand it. In your assignment you will get some questions like this. Okay, whenever you do the assignment, you should have clear understanding, and in your test you will get some questions from there. And in our next lecture I hope to explain the deletion process. Deletion is more difficult. It has 4 to 6 different
Are you gonna do
conditions.
attendance?
Oh, give me 1 more minute, please. Let me take that on this. I forgot. Thank you so much. Let me take that in this.